In the last lecture, we had discussed about the design of gauges, limits, and fits. Uh, we had covered the basic terminology related with the limits and fits. Then, what are the limits of the sizes? Because we know that uh, each each manufacturing size will have or each manufacturing component will have two sizes. One is upper limit and another is a lower limit, because it is impossible to uh, produce the components consistently with exact dimension. So many variables will contribute uh, towards the natural variability. Then we have seen meaning of deviation. Then what is a lower deviation, what is upper deviation, so that we have seen. Both the deviations are applicable to hole as well as shaft. So hole will have lower deviation as well as upper deviation. Shaft will also have lower deviation as well as upper deviation, and it is not necessary that both hole and shaft should have same amount of deviations. It may be different. It depends upon the what kind of fit is required. Then we have seen this terminology, what is a zero line, what is a tolerance. Then we have discussed about this entire say sketch that is discussed. Then uh, we have up to this we had discussed yesterday. Now we have to see what are the positional tolerances. So basically there are two types of the positional tolerances. Means our tolerance is the difference, as we have seen yesterday. Tolerance is nothing but the difference between the maximum size of part and a minimum size of the part. The size of the part is going to vary between these two sizes only, and the difference between these two sizes, that is maximum size and minimum size, is called as a tolerance. Now as you can see, there are two types of the tolerances, that is a unilateral tolerance and bilateral tolerance. So unilateral tolerance, as you can see, there are two sketches, sketch A and sketch B. So sketch A shows the unilateral tolerance, sketch B shows the bilateral tolerance. So in the name itself the definition is hidden, unilateral. So uni means one, single. So the tolerance which is given only on one side of the basic size. So you can see when the tolerance is on one side of the basic size, it is called as a unilateral tolerance. So as you can see here in this part, this is one shaft is there, and it's, you can see the size how it is mentioned. It is a 20 plus 0.000 and minus 0.004. So you can see the tolerance is on the lower side, that is a negative tolerance is there, no positive tolerance, it is 0, 0. So here the tolerance is only on one side. It may be on lower side or it may be on upward side, but it is going to be only on one side in case of the unilateral tolerances. But there is one more case here. This is the shaft again. Here the size is mentioned as 20 plus 0.002 and 20 minus 0.002. It means here this is the basic size, 20 is the basic size. So here the tolerance is given on both the sides, that is on positive as well as negative. So the size of this particular shaft is expected between 20 plus 0.002 and 20 minus 0.002. So any size between these two limits is accepted. So this is the case of the bilateral tolerances. So whether to go for unilateral tolerance, whether to go for bilateral tolerance, it is totally depending upon what is the final application of that particular component, where this part, where this where the designed part is going to be fitted, depending upon the sizes of the opposite component in which this component is going to be fitted. Those are also important. So depending upon the dimensions of mutual components, the tolerances are decided depending upon the kind of function that is required to be done by that particular assembly, decides the positional tolerances. Then what is the meaning of fit? So fit is nothing but when two parts are to be assembled, when two parts are to be assembled, the relation resulting from their sizes before assembly is called a fit. Before assembly it is called a fit. So one example is shown. This is a shaft, this is a hole. The sizes of shaft are given 1.495 and 1.493. These are the two extreme. This is a minimum size, this is the maximum size of the shaft. Then similarly, this is the hole. The maximum size of the hole is a 1.502. The minimum size of the hole is a 1.500. These are the two possible extreme sizes of the hole. Therefore now the fit is nothing but it is the assembly of these two parts, that is, one is shaft, another is hole. And now we know that the size of the shaft can be vary between any of these sizes, that is, it can vary from 1.493 to 1.495. also it can vary from 1.500 to 1.502. So now the relation resulting from the sizes of this hole and shaft is called as a fit. Means this can get cleared in next few slides, but whatever is this relation, that relation is nothing but from the sizes before assembly. Okay, so before assembly takes place, you have to decide what is the difference between size of the hole and the size of the shaft. So there are various possibilities are there. So we can see those possibilities, and that relation is called as a type of the fit. So let us take say example of the, there are basically three types of the fits are there. This is a very important concept from oral point of view. Many times the question is asked at the time of the oral, what is a clearance fit, means what is a transition fit, what is a interference fit. Just elaborate with the help of the some examples. So as you can see, first type of the fit is a clearance fit. So as you can see, there is a clearance between size of the hole and size of the shaft. So in case of the clearance fit, as you can see, there are two rectangles are shown. This is one rectangle you can see, and this one is another. Okay, so this larger rectangle correspond to it shows the various sizes of the hole, and the smaller rectangle represent the sizes of the shaft. So in case of the clearance fit, the size of the hole, or you can see this correspond to size of the hole. So as we know that the hole will have two sizes, any part, any component will have two sizes. So one is size from here to here, you can see this is the minimum size of the hole. If you measure the distance from here to here, this is called as a minimum size. Then distance from here to this much, okay, this much line, so that is the maximum size of hole. So the hole will have minimum size, as well as the actual size of the hole can vary between minimum size to maximum size. Okay, similarly the shaft, here this is the shaft. Okay, the size of the shaft also can vary between from this to this is the maximum size of the hole, upper limit of the hole or upper maximum limit size of the hole, and this is the minimum size of the hole. Here distance between this line and this line is the minimum size of the shaft. Distance between this line and this line is the maximum size of the shaft. The difference between the maximum size of the shaft and minimum size of the shaft is nothing but this is the tolerance of the shaft. Similarly, this hatched portion in red color is the maximum is the tolerance of the hole. Now as you can see, in case of the clearance fit, the minimum size of the hole is, this is the minimum size. So minimum size of the hole is always going to be larger than the maximum size of the hole. So this line, this size is always greater than this size. So minimum size of the hole is larger than maximum size of the shaft in any condition. Okay, so what are the possibilities? The size of the hole, it can happen that the size of the hole, the hole is at its minimum size and the shaft is at its maximum size. So this is the difference between now size of the hole and the size of the shaft can be considered as a clearance. So this distance between minimum size of the hole, this, and maximum size of the shaft, so this much distance, this much from here to here, that is the minimum possible distance between size of the hole and the size of the shaft. That's why it is the minimum clearance. This difference is positive. The difference between size of the hole and the size of the shaft, if it is a positive, then it is called as a clearance. So this is the minimum positive difference. So this is a minimum clearance. There is a one more possible. There are many possibilities. So we are discussing the extreme condition. There is a possibility that the size may attain the hole may attain the maximum size. So distance between this to this, and the shaft may attain minimum size from here to here. So in this case, the difference between maximum size of the hole, this one from this line to this line, and a minimum size of the shaft, that is this line to this line, so that difference is nothing but it is the maximum clearance. Again it is positive. So this is a maximum positive difference between size of the hole and size of the shaft. This distance from here to here, that is the minimum positive difference between size of the hole and shaft. So in any extreme cases, this difference is positive, means the minimum size of the hole, this one from here to here, minimum size of the hole is larger than maximum size of the shaft. So this line and the distance between this line and this line, so this is always, this distance from here to here, maximum size of the hole is always minimum size of the hole is always greater than maximum size of the shaft. So if this condition is happening, if this condition is satisfied, then it is called as a clearance fit. Okay, this is a clearance fits. Depending upon the amount of clearance, there may be different clearance fits are again subdivided as a sliding fit, easy sliding fit, a running fit, depending upon this difference. Then there is another fit, that is a interference fit. Now this interference fit is exactly opposite the clearance fit. In case of the interference fit, the difference between size of the hole and size of the shaft is going to be negative. It is going to be negative. So as you can see, again we can discuss here. Suppose this is the hole, left one, this hatched portion, so this shows the size of the hole, This shows the sizes of the shaft. So as you can see in this case, uh, distance between this line and this line, it is the minimum size of the hole. Similarly, distance between this line and this line is called as the maximum size of the hole. Okay. Similarly, coming to the shaft now, this portion on the right side, distance between this line and this line is the minimum size of the shaft. Similarly, distance between this line and this line is the maximum size of the shaft. Okay. Now, similar to last definition, that is a what is the minimum difference between the size of the hole and the size of the shaft. Now we can say that the difference between maximum size of the hole, you can say this distance, maximum size of the hole, and minimum size of the shaft, that is this distance from here to here. So difference between this distance here to here and this distance, maximum size of the hole and minimum size of, this is the minimum size of the shaft. So this difference is actually, it is a negative. You have to subtract the size of the shaft from the size of the hole. So here this difference is a negative. So that's why if this difference is a negative, then it is called as a interference. So this difference is at, it is the minimum difference, isn't it? So that's why it is called as a minimum interference. So distance between this line, that is the maximum size of the hole, and this line, this one, it is the minimum, this line, minimum size of the shaft. Okay, so that is called as a minimum interference. Similarly, there is one more possibility, the difference between minimum size of the hole, so this distance, this is the minimum size of the hole, and the maximum size of the shaft, that is the distance between this line and uppermost line. So this distance from here to here, it is the maximum size of the shaft, this is the minimum size of the hole. So the difference between minimum size of the hole and maximum size of the shaft is called as the interference, maximum interference. The interference is not going to be more than this. So if you observe this clearly, in this case, the maximum size of the hole here is always going to be less than minimum size of the shaft, maximum size of the hole. So this one is always going to be less than minimum size of the shaft. Then it is the case of the interference fit. It is the case of the interference fit, and the difference between size of the hole and the size of the shaft at any condition is going to be negative. Okay, so examples are shrink fit, heavy drive fit. It depends upon the amount of interference. Then transition fit is in between the clearance fit and the interference fit. So it depends, in this type of the fit, the limits for the mating parts are so selected that either a clearance or interference may occur depending upon the actual size of the mating parts. So as you can see here, the transition fit, here various possibilities are there. So in case of the transition fit, as you can see, this corresponds to shaft, this corresponds to hole. Okay, so there is a possibility that in this case, here this distance from here to here or from here to here, this is the minimum size of the shaft. Distance between this line and this topmost line, it is the maximum size of the shaft. Okay, similarly, these bearing sizes are correspond to sizes of the hole. So distance between this line and this line, it is the minimum size of the say hole. Then distance between this line and this line is the maximum size of the hole. Now as you can see here, in this case, in case of the transition fit, the minimum size of the hole is always going to this size, minimum size of the, sorry, minimum size of the shaft is always going to be less than minimum size of the hole. Okay, it is always going to be like this. So minimum size of the shaft is always going to be less than minimum size of the hole. Also you can define it in other possibility also. The maximum size of the shaft, you can see this is the maximum size of, means this distance from here to here, the maximum size of the shaft from here to here is going to be larger than the minimum size of the hole. Okay, so this distance from here to here is always larger than this distance. Okay, so if this condition is there, then you can say that this is the case of the transition fit. Now depending upon the actual situation, there may be clearance fit or there may be interference fit. For example, you can say that if the shaft is at its minimum conditions, say the shaft size is this one, okay, and the hole is at its this condition, minimum size, then also we can see the difference between size of the hole and the size of the shaft, it is positive. So this distance from here to here is larger than this distance, then this is the this difference is positive, so it is a clearance fit. But there can be, it is not going to be always, the condition is not going to be always like this. It may happen in different case also, that the size of the hole is this one. It may happen the hole is at its minimum size and the shaft is at its maximum size, say it may be from here to here. So in this case, the minimum size of the hole is less than maximum size of the shaft, so the difference between size of the hole and the size of the shaft is negative here. That's why the fit resulting in this case is interference fit. Okay, so that's why the transition fit is nothing but it is in between the clearance fit and interference fit. Now the fits are designed, there are two concepts, that is a hole basis system and shaft basis system. So what is a hole based system and shaft based system? So in this system, so first is a hole based system. So in hole basis system, the size of the hole is kept constant and different fits are obtained by varying the shaft size. So you can see, we will say try to explain this definition now. You can see this line from here to here shows the size of the hole. So these three lines, 1 2 3 lines are corresponding to the sizes of the hole. Okay, this from 1 2 and 3, these three lines show the sizes of the hole. Now in case of the hole basis system, if you want to achieve the different fits, that is clearance, transition and interference fit, if we want to achieve these fits, we have to achieve this by varying the sizes of the shaft only. So if you want the clearance fit, this type of the fit, clearance fit, so you have to choose the shaft which is a lesser in dimension than the size of the hole. Okay, so here in this case, in clearance fit, the size of the shaft is going to be less than the sizes of the hole. Okay, then in case of the transition fit, again if you want transition fit, again you have to change the dimension of the shaft, not the hole. The size of the hole is going to be constant, always remember that, in case of the hole based system. So here as you can see, the size of the shaft is chosen such a way that the transition fit is obtained. Third one, interference fit. So in this case also, the size of the hole is kept constant and the size of the shaft is chosen in such a way that interference fit is obtained. So in case of the hole basis system, the size of the hole is kept constant, whereas the sizes of the shaft are changed according to the type of the fit required. So please remember this, because this question is asked at the time of the oral also. What is a hole based system and what is a shaft based system, and adding to that which system is preferred in the industries, whether hole based system is preferred or shaft based system. So we will discuss that part in last class. So then there is a shaft based system. So in case of the shaft based system, again there are opposite to the hole based system. In case of the shaft based system, the size of the shaft is kept constant. So you can see this 1 2 3. So these three lines from here to here, these three lines, this represents the size of the shaft. Okay, and these three 1 2 3 denotes the various types of the fits corresponding the size of the hole. So you can see in case of the shaft based system, in order to obtain the different fits, the size of the shaft is kept constant and the sizes of the hole are varied. So in order to get the clearance fit, choose the hole size in such a way that this is the hole size from say this to this. Okay, the hole is chosen larger, the sizes of the hole are larger than the sizes of the shaft. Okay, this distance is less than either this distance or this distance. Similarly, for transition fit also, choose this shaft the hole size so that transition fit is obtained. And in case of the interference fit also, you can see these are the sizes of the hole 1 2. So from here to here minimum size of the hole, from here to here maximum size of the hole, whereas from here to here minimum size of the shaft, here to here maximum size of the shaft. So you can see the difference. In this case, in this particular condition, the size maximum size of the hole is less than minimum size of the shaft, so you are going to get the interference fit. So in case of the shaft based system, the size of the shaft is kept constant, whereas the sizes of the hole are varied to get the different types of the fits. So basically now the question arises, which type of the again you can see this is again elaborated here. So this is the hole based system. So you can see in case of the hole based system, this particular rectangle from here to here, which is say slightly bluish in color, so it represents the size of the hole, and various fits obtained are clearance fit. So you can see in clearance fit, the size of the hole is larger than the sizes of the shaft. Clearance fit. Transition fit, various possibilities are there. So this is possible, this is possible, this is possible. So all these three are cases are the possibilities of the transition fit, isn't it? And then third one is the this corresponds to, in this case this is the interference fit. Here the sizes of the shaft are larger than the sizes of the hole. So you can see in this case various fits, that is clearance, transition, interference, are obtained by just varying the sizes of the shaft only, whereas the in all three conditions the size of the hole is constant. Reverse to that, this is a shaft based system. So this rectangle shows the rectangle in bluish shows the size of the shaft which is kept constant, and now there is a various fits, that is a clearance fit. Here the size of the hole is larger than the size of the shaft, clearance fit. Thus then this is the transition fit. Okay, and this is the interference fit. Here this is the size of the hole which is less, or which is less than the size of the shaft. That's why it is an interference fit. So now what is the which kind of system is preferred in case of the in industries? So in industries, the hole based system is always preferred. Please remember this. In case of the hole based system, in industries, hole based system is always preferred than the shaft based system, because it is easier to produce the shafts of different sizes than to produce the holes of the different sizes. Because if you want to produce the shafts of different sizes, you can attach that you can mount the shaft on say lathe machine, and you can take the different cuts with the help of the cutting tool, and we can make the shaft of any sizes. But that is not the case with the manufacturing of a hole. If you want to manufacture the hole, you have to use first drill, and then you have to go for the rims. So if you want say n type of the holes, then you will require n type of the reamers. Okay, and it is economically it is impossible, or economically it is very difficult to keep the n number of reamers in your stock. It will increase your cost. So it is better to go for the shaft based system. So that's why shaft based system is preferred in case of the in industries. Now in case of the hole basis system, always remember that lower deviation is 0. That is a minimum hole size is equal to basic size. In case of the shaft based system, so we have just seen the hole based system and shaft based system. So as you can see, if you go to this sketch again, so let us see this sketch. If in case of the hole based system, the fundamental deviation or the lower deviation is 0, so this size, okay, this size from here to here, so minimum diameter of the hole, this one, is going to be equal to basic size, this basic size. So this distance and this distance is going to be same, so this line is going to overlap here. Okay, that's why obviously the distance between this line and minimum diameter of the hole or minimum size of the hole, that is going to be 0, because this line is going to overlap here. That's why this lower deviation, which is referred as a fundamental deviation of the hole, is going to be 0. It is going to be 0. So fundamental deviation is the deviation corresponding to the size which is closer to basic line. So for a basic size, for example, this line is the distance between this line and this line is the fundamental deviation for the hole. Okay, whereas the distance between this line, upper line, and basic line is the fundamental deviation of the shaft. Okay, so in case of the hole, in this particular condition, in this case, the fundamental deviation of the hole is nothing but the lower deviation, this distance, it is close to the basic line. Whereas in case of this shaft, the fundamental deviation is nothing but the distance between this line, upper limit of the shaft, and the basic line, basic size. So in this case, in case of this particular shaft, the upper deviation is the fundamental deviation. Okay, so in case of the hole based system, the fundamental deviation is going to be 0, whereas in case of the basic whole shaft based system, the fundamental deviation of the shaft is going to be 0. So this distance is going to be 0 in case of the shaft based system. Fundamental deviation is going to be 0. So coming back, can see, so in case of the hole basis system, lower deviation is 0. That's why minimum hole size is equal to going to be equal to basic size. In the example that we have seen, fundamental deviation is going to be 0. That is the maximum shaft size is going to be equal to basic size. Now IS system for specifying limits and fits. What are the IS systems for specifying limits and fits? So there are whenever we are deciding the limits, fits, and tolerances, there is a range of deviations and tolerances are given for basic size. There are 20 types of the manufacturing grades, that range from 01 to 1 to 18. So 20 types of the manufacturing grades are there. And there are 28 types of the fundamental deviations are there. Just we have seen the fundamental deviation. So fundamental deviation decide the position of the tolerance zone. So I will explain that in the next slide. There are 28 types of the fundamental deviation and 20 grades. So these grades decide the amount of tolerance for a particular part. The grades decide the amount of tolerance for a particular part, and this fundamental deviation decide the position of this tolerance. So this grades decide the magnitude of the tolerance zone, and fundamental deviations decide the position of the tolerance zone. Okay, so basically there are 28 fundamental deviations. So capital letters, so these fundamental deviations are denoted by some letters. So if these letters are capital letters or block letters, it indicates that fundamental deviation is for the whole. So capital letters denote the fundamental deviation of the holes. Small letters denotes the fundamental deviation of the shafts. So we can see one example, method of indicating the part sizes and fits. So for example, if you see that this is a one fit is there, that is a 50H7H9. So what is the so this is one of the method to indicate the type of the fit. So what it indicates, or what is the meaning of this 50H7H9? The meaning of 50H7H9 is that 50H7 indicates a hole. So we can say that, as we discussed, there are basically 5 attributes of this, 5 parameters of this particular fit. In this, 50 indicates the basic size, H indicates the fundamental deviation for the whole because it is a capital letter. Okay, 7 indicates the tolerance for the whole. So this 7 is associated with the capital H. Then this is a small h, so it indicates the fundamental deviation for the shaft because it is a small letter. And 9 indicates the tolerance. 9 is nothing but IT9, international tolerance grade 9. It indicates the tolerance for the shaft. So here we can say that 50H7, it indicates a hole. It indicates H is a hole. It indicates a hole with basic size 50. So this 50 is the basic size of the hole, and the manufacturing tolerance of IT7. So we are going to see what is this IT7. So you just remember, it is an international tolerance grade for 7. So this is the tolerance while manufacturing the whole of this size 50H7 is IT7. So similarly, 50H9 indicates it is a small letter, that's why it is a shaft. It indicates a shaft with a basic size 50 mm and manufacturing tolerance IT9, that is international tolerance grade 9. So this number is different, 7. This number is different, IT9. So here if we compare the tolerance of the hole, so the tolerance of the hole is IT7, tolerance of the shaft is a IT9. So here we can see that tolerance for the shaft is larger than the tolerance for the hole. It is not necessary that the tolerance of for the hole and tolerance for the shaft both should be same. It is not necessary at all. So there are some examples, means you may have the question that which kind of fit is used, where it is used, and what kind of fit is what kind of clearance is maintained. So there is one example is there, as you can see, if there is a clearance fit is there, so assembly very easy by hand. So if you take capital H type of the hole and small e type of the shaft and IT7 H7 type of the hole and E8 type of the shaft, then you are going to get the assembly which can be very easily done by the hands. Okay, so example of utility where it is used, parts which necessitate high clearance, where you want high clearance, there you can use this type of the you can choose different the combination of this type of the hole and this type of the shaft. Then H7 F7 easy by hand, assembly easy by hand, parts rotating in bushing. Okay, then this H7 G6 reasonably easy by hand, sliding, parts accurately guided. H7 H6 possible by hand, accurate fixed assembly. So everywhere in this clearance pit you can see the assembly is possible just either by hand very easily or with some efforts. Now transition fit H7 K6, you can see the side we have taken this as a hole based system. You can see from here every time the hole is constant, you can see H7 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 H7, whereas E F G H K, these are the different shafts, small letters are there. So hand if you want to carry out this type of the assembly, you have to use either hand or you will need to press the assembly when the transmission of the little force is needed. When you require this transition pit, when you want to transmit little amount of force, when you transmit little amount of force. Similarly, then there is a press fit. So again H7 P6, so use a press when the transmission of great deal of force. H7 S6 by expansion, means what you have to do in this case, remember that the size of the shaft is going to be greater than the size of the hole. Then if the size of the shaft is greater than the size of the hole, how you are going to do the assembly? Just imagine one hole is there, one shaft is there, and your objective is to fit that shaft in the hole, but the size of the shaft is greater than the size of the hole. Then how you are going to carry out the assembly? So in this case, what is done here, the hole is locally heated, the hole is locally heated. So what happens, the due to the heat, the size of the hole will get increased, it will expand, isn't it, for some time, and at that time you have to insert the hole. So as you insert in this heated hole, you have to insert the shaft. So since the size of the hole is increased, it will get easily fitted. But after some time, when the metal gets cooled, or when the hole gets the component with that hole gets cooled, it will again shrink and its sizes will again come to its original position. So this is a practical way to carry out the assembly. So here you can disassembly is impossible without damaging parts. So if you want to remove this type of the fit, this shaft and hole, if you want to dismantle these two parts, so it is not possible to do easily. So it is not possible without the damaging parts. Then rotating shafts, so H7 and K6, so here outer raise by hand, inner raise by light press, follows the bearing theory concept. Okay, rotating housing again, so various combinations are there. So depending upon the application where you want here, there is a concept of bearing. Okay, so depending upon what is the application of your assembly, the type of the fit is chosen. Okay, then fundamental deviations, as I told you that these fundamental deviations, there are 28 types of the fundamental deviations for hole as well as shaft. So you can see this is the zero line. Okay, so holes are designated by the capital letters. Okay, A to Z oversized holes. So you can see A, B, C, C, D, D, E, F, F, G, G. So up to this, from capital A to capital G, these these are the different. A is a different type of the hole, B is a different type of the hole, C is a different type of the hole. So everywhere you can see, in this case they are called as oversized holes. Means here in each case, each hole is a the size of the hole is always greater than the basic size. You can see this is the basic size. So sizes are measured from this reference. Remember that one reference line is there. So from here to here, the basic size here, from distance between this line and this line. So in this case, if you take the example of A type of the hole, the A type of the hole this is greater than the basic size. So if you take the example of G type of hole also, here also the G type hole, the sizes of the G type hole are larger than the basic size. That's why they are called as a oversized holes, A to G. Okay. Similarly, letters P to ZC, you can see here, say P to ZC, they are coming. Now all these holes A to Z are above the basic line. Here you can see this is the basic line. So here to here, all the holes, okay, are above the basic line, whereas P to ZC all are below the basic line. That's why they are called as a undersized holes. Here from P to ZC, the size of the hole are lesser than the basic size. Okay, so all the letters, if you count these letters from count these holes from A to ZC, these are 28 types of the holes. Okay, 28 types of the holes. So for A type of the hole, you can see the fundamental deviation is nothing but distance between basic line and this line, lower line, and this distance is positive. Okay, for B type of the hole, again this distance is positive, but A type of the hole, for A type of the hole, fundamental deviation is larger, you can see, from here to here, as compared to B type of the hole, C type, and it will go on decreasing, and again it will become negative. Okay, so similar to this hole, these shafts are designated by small letters. So you can see small letters A, B, C, D, like this. Similar to this, you can say this is a exact mirror of these blocks, which are shown as a solid filled black. They are filled in black. So these are the fundamental deviations of the shaft, and they are exact mirror image of this one, fundamental deviation of the hole. Okay, so they are exactly opposite to the fundamental deviation of the hole. So you can see this is A type of the shaft, B, C, C, D, D. So you can see this is A type of the shaft, this is A type of the hole. So here you can see this is the fundamental deviation of the A type of the shaft is distance between basic line and this line. Okay, so as you can see, it is here also, you can see here also, this is the A type of the shaft. So distance between this line and this one, it is the fundamental deviation. So A, B, so from A to G, you can see from A to G all the shafts are below the basic line, below the zero line. This is the zero line, isn't it, which is common. So below the zero line, A to G, so all these are called as a undersized shaft, undersized shafts. Whereas from P to ZC, okay, P to ZC, they are the P to ZC, they are called as oversized shafts because they are above the basic line. Okay, above the basic line. So similar to the hole size P to ZC, P to say M to ZC, not P to ZC, it is M to ZC. They are called as oversized shaft, and A to G are called as a undersized shaft. Now this H letter has got huge importance in this limits, fits and tolerances, H is used for the hole such, and H is used for the shafts also. Capital H is used for holes, so this one. Small h is used for shafts, this one. So if you capital whose fundamental deviation is 0. So fundamental deviation is 0 means what? You can see this in this sketch. So this is H type of the hole. So for H type of the hole, you can see the for H type of the hole, this line, this hole will have two sizes. One size will correspond to this line, another will correspond to this line. So in this case, the fundamental deviation for the H type of the hole is 0. That is the, say for you take the example say of B type of the hole. So for B type of the hole, the fundamental deviation is this distance E1. E1 is the fundamental deviation for the B type of the hole. So there is some value. But for H type of the hole, this difference E1 is 0. You can see this line is over, overlapping the 0 line. That's why the difference between 0 line and minimum size of the hole is 0. That's why it is called as the H is a, it is a hole with the fundamental deviation as 0 for this. Okay. Similarly, H is a shaft whose small h is a shaft whose fundamental deviation is 0. So you can see here H, this is the shaft. For this H shaft, fundamental deviation. So again you can see here fundamental deviation for, let us take the example of B type of the, this is the B type of the shaft. So fundamental deviation for the B type of the shaft is nothing but the difference between this 0 line and this line. So this distance is some finite value. This distance is 0 in case of H type of the shaft. You can see here H type of the shaft, this line, this one is over, it is overlapping this basic line. Okay, that's why the difference between maximum size of the shaft and basic size is 0. That's why it is a shaft, it is a shaft with 0 deviation. So H, whenever there is a H letter is there, either in case of the hole or in case of the shaft, always remember that those parts are having fundamental deviation as 0. Now there are various ways how to calculate the fundamental deviations for the shafts. Some formulae are given. There is no need to remember these formulae. These formulae will be given you at the time of the exam. The fundamental deviation will be given. So you can see formulae for the, what is this table? This table shows the formulae for the fundamental shaft shaft deviation for the shafts up to 500 mm diameter. So you can see there we have just seen there are 28 types of the shafts. So you can see on in this column A, these are the shaft designations, that is A, B, C, D up to ZC, isn't it? So for A to G type of the shaft, the fundamental deviation is negative. We have just seen, isn't it? We have just seen. So for A to G type of the shaft, from A to G, all are below the basic line. That's why they are going to be negative. So you can see here for A to G type of the shaft, the fundamental deviation, this is the value of the fundamental deviation, it is negative. You can see negative sign is there, negative, everywhere you can see the negative value. So this value will be given to you at the time of the example. Depending upon what kind of fit is given to you, related to that the fundamental deviation will be given to you. This fundamental deviation is in microns. Please remember this. It is in microns. It is shown here. It is in microns. When capital D is in millimeters. So now what is this capital D? That is very, very important. So whenever we are going to discuss this the design of the limit gauges in detail, so we are going to discuss it in detail uh, so here as you can see it is in microns, for D is in millimeters. So D is one diameter step. So what is that diameter step that I am going to discuss in the coming lectures. If D is in millimeters, for in this formula the one capital D is there in each formula, isn't it? So that D has to be taken in millimeters, and when you take that value in millimeters, this D, then the fundamental deviation you are going to get is, it is going to be in micron. This has to be remembered very strictly. D is in millimeter, then only the fundamental deviation is going to be in micron. 1 micron is equal to 10 raised to minus 3 millimeter. Similarly, for H type of the shaft, the fundamental deviation is going to be 0. We have just seen. Okay. Then for after that, from J to ZC, the fundamental deviation is positive. You can see here. Isn't it? Fundamental deviation is going to be positive, because again we have seen for say M to ZC type of the shaft, the fundamental deviation, all the shafts are above this basic line, basic size, or above the zero line. That's why they will have positive value. Whatever is above this zero line, that is going to be positive. If the fundamental deviations are below the basic size or below this zero line, that is going to be negative. That's why M to ZC, it is a positive value. It is having positive value. So as you can see, M to ZC, it is a positive. You can see everywhere. So this is just for your information. There is no need to memorize this table. This is just for your information. This value will be given. Then you might be asked how to decide the tolerance grade. So one table is given. Again, this is not necessary to be remembered. IT01 grade, then it is IT01. We have just IT01 to IT1, high quality work, then inspection standard, workshop standard. IT2 to IT5, values of the tolerance selected between IT2 and IT5 are again high quality range. Then you might have learned these are the manufacturing process. So remember that this manufacturing process, for this manufacturing process, this much amount of the tolerance is given. So this is the tolerance and this is the manufacturing process. So lapping, it is not grading, it should be grinding. Okay, so there is a mistake is there, grinding. Then IT6, the value is a 10I. Now what is this I? I is called as a fundamental tolerance unit. So how it is to be calculated, that we are going to see separately. So in each case, say from IT6 to IT16, you can see 10I, 16I, 25I. So everywhere there is a I, that is a fundamental tolerance, and that is multiplied by some number. Okay, that is multiplied by some number. So you can see. So you can, so for IT6 is used in case of the boring, 16I lathe and honing, then automatic lathe, capstan lathe, milling and slotting, casting. So for casting 400I, forging, then actually I think there is a slightly some mistake is where I have to check. Okay, okay. So what you can see, casting is there, then forging and flame cutting. So as you go towards the you can say these from, you can say say grinding to this upper size, grinding to high quality work, it is highly finish will be there. That's why tolerance is very less. But as you go towards some say common processes, say boring, lathe, then drilling, press, casting, forging, the tolerance is, it is not possible to achieve the high amount of tolerance. So sorry, it is not possible to achieve the close tolerances. That's why the larger tolerances are given in case of the casting, forging and flame cutting. So you can see here there is one, we are going to see this in detail. I is a fundamental tolerance factor. I is equal to 0.45 cube root of d plus point not 1 d. This is the formula which is to be memorized. You have to remember this formula. It might happen that in sometimes this formula is given to you in the examination, and sometimes in it may not be given to you. So please remember this formula. It is mandatory that you memorize this. Don't expect that this formula will be given in the exam. Sometimes it may be given, sometimes it may not be given. So that formula is to be kept in mind, where d is a geometrical mean of the diameter step. So some diametrical steps are considered in when limit speeds and tolerance grading system is designed, and these are the values of the tolerance grades. So for IT5 there is a 7, IT6 10, I just we have seen, and you can calculate the standard tolerance for any process. So we are going to see this in detail. These are the gauges. Then the we'll try to see what is okay. Then last part of this gauges or Taylor's principle. I want to discuss this Taylor's principle. So what is this Taylor principle and Taylor's principle of gauge design? So in the last lecture we have seen that whenever the gauges are basically used to check the two sizes, that is we just discussed that every part will have the two sizes. Okay, one size is considered as a minimum size, and another is going to be the maximum size. So the size of the part is going to vary between these two limits only. So one is a maximum limit and another is a minimum limit. So if you take the example of this one hole is there. Okay, so there is a possibility that this is the hole. Okay, so the size of the hole is going to vary between this size, say size A. Okay, so we can say that it is the minimum size of the hole, isn't it? So size A corresponds to minimum size. I am talking about the diameter only, I am not talking about the length, remember that. Okay, so A denotes the minimum size of the hole, whereas B denotes the maximum size of the hole. So as per our definition of the say part sizes, A is the minimum size of the hole and B is the maximum size of the hole. If we correlate this with the metal condition, what amount of metal is remaining in a part. For example, we can say that when the size of the hole is at its minimum condition, so A, when the hole attains the size A, that is when the hole is at its minimum size, in that case the material, what is the amount of material remaining in this part? It is this one here and here. So maximum amount of material is remaining in the part when the size of the hole is minimum. This is for the minimum size of the hole. So when the hole is at its minimum size, there is a maximum metal in that particular part. Okay, and opposite to that, when the hole is at its minimum size, when the hole is at its maximum size, there is possibility that the hole may have this size B. So when the hole is at its maximum size, the minimum amount of material is remaining in this part. Okay, so we can say the maximum metal condition and minimum metal condition. So when the hole is at minimum size, there is a maximum metal condition. When the hole is at its maximum size, there is a minimum metal condition. And the go and no go gauges that you have designed, these gauges check both these conditions. Okay, so we know that how to decide whether this has been discussed in the last lecture also, how to decide whether this whole this whatever you have manufactured, whatever hole you have manufactured, whether it is okay or not okay. What is the basic principle? We have discussed that. In basic principle we have discussed that whenever we are checking the components with the help of the limit gauges, we have there two conditions have to be satisfied simultaneously. That is, go end of the gauge must go, or it must pass through this hole or through the shaft, and no go end should not enter the hole. So if both the conditions are satisfied, then and then only we can say that this hole is correct or this dimension is okay. So as per the definition, the go end must go at this position, and the no go end should not enter here. So what is told by the tailors? So according to Taylor, what the Taylor is saying, the Taylor says that what the Taylor says, the go end of the gauge. So suppose let us say that we have to certify this hole whether it is okay or not okay. So one go end, one gauge is one gauge you have designed. This is the go end of the gauge, and this is the, let us say this is a there is a no go end of the gauge. So if you try to insert this end here in this hole, so it must pass, and if you try to insert the no go end, it should not pass at all, it should not enter at all. If both these conditions are satisfied, then and then only this hole is correct. But according to Taylor, what the Taylor is saying, Taylor says that you have to design the go end of the gauge in such a way that it should cover the entire surface to be tested. For example, if capital L is the length of the hole to be tested, then if capital L is the length of this hole to be tested, then the length of the go end, of the gauge must be also minimum equal to L. Minimum length of the go end of the gauge must be equal to L. For example, if this hole, the length of this hole is say 100 mm, if the length of the hole is 100 mm, then according to the Taylor, the length of the go end of the gauge that you have designed, it should be minimum 100 mm. So it should cover the entire surface of the hole to be tested. It must cover the entire length of the hole to be covered. This is the principle of the Taylor. Also, this is as far as the go end is concerned. Go end, always remember that go end always checks the maximum metal condition. The go end of the gauge always checks the maximum metal condition, whereas the no go end always checks the minimum metal condition. So according to the Taylor, the no go end should not be made in cylindrical form. This is the cylindrical shape of the go end. We have just seen the gauge. You can see these are the gauges. This is a say let us say, take the example, this is the plug gauge that you are using to check the hole. So let us say this is a go end and this is a no go end. So if you try to see the shape of this the go and no go end, they are cylindrical in shape. Okay, let it be go end or let it be no go end, both are cylindrical in shape. But according to the Taylor, the no go end shape should not be cylindrical, rather it should be made in terms of the two sharp points. It is very important. The no-go end, the shape of the no-go end should be two sharp points. It should not be cylindrical in shape at all. Okay, so basically two important conditions or two important things the tailor has put. The go end of the gauge must completely cover the surface to be tested. Therefore the length of the go end should be minimum equal to the length of the hole to be tested, or length of the shaft to be tested, whereas the no go end should be made in the form of two sharp points instead of making it in cylindrical shape. These are the say statements of the Taylor's principle. Now let us check the how it works and why he has made. So whatever we have discussed, go end of the gauge must be of the perfect form made to maximum metal condition. It must completely cover the surface to be tested. So we have seen this go end must cover the surface to be tested. Entire surface has to be covered by this end, go end. Okay, whereas no go end must comprise of the 2 points to make sure that no portion of the workpiece is outside the minimum metal condition. So no go end should be made in terms of the two sharp points. Don't make it cylindrical. This is a cylindrical shape, so no go end should not be cylindrical. It should be made in terms of the sharp points. So you can see for the plug gauge, the go end, this is the plug gauge is used to check the sizes of the hole. So this whatever is hatched portion, so that is a part size. So this is a hole. So if you want to check the hole, plug gauge is used, go end, no go end. Similarly for the snap, for this is the shaft, to check the shaft, snap gauge or ring gauge or gap gauge is used. So this is the go end of the shaft, go end of the gauge, and this is the no go end of the gauge. Okay, so you can see that. Now we'll try to why Taylor has mentioned that, because now you take the example. I will tell you very simple example why the Taylor has insisted to have the no go end in the form of say sharp points. Let us now take the example. Let us now consider that this is the hole which is actually produced. You can see one ellipse. This is the ellipse. Okay, this is the ellipse which has been actually manufactured by somebody, and you want to check whether this hole produced, whether it is okay or not okay. Actually speaking, this hole, if you check this by the gauges, it should be rejected, because we want perfectly circular hole, and this hole which is actually manufactured, it is not circular, it is elliptical hole. Now let us see if what is happening if Taylor's principle is not followed. Okay, now let us say that there are two possible conditions, two possible sizes. We know that this inner circle represents the minimum size of the hole. This is the hole to be tested. So this whole inner circle represents the minimum size of the hole, means it is the maximum metal condition. So inner hole represents the minimum size of the hole. Outer bold circle represents the maximum size of the hole. So inner bold hole represents the minimum size of the hole. Outer circle represents the maximum size of the hole. So minimum size of the hole corresponds to maximum metal condition, and maximum size of the hole represents the minimum metal condition. There is a, please don't get confused between size and metal limit. Okay, so we know that go end checks the maximum metal condition, and no go end checks the minimum metal condition. So you have let us assume that you have cylindrical type of the gauge. Let us say that you have this type of the gauge. So one end is, let us say this is a go end and this is a no go end. So what you will do, you will insert this go end in the hole. Okay, so this is the hole. You will insert that cylindrical hole here. You will insert that go end of the gauge here. Now will this go end pass in this condition? Yes, it is going to pass, because this is your actual elliptical hole. So this elliptical hole, its size is not, in any case the minimum size of the hole is not below the minimum metal, it is not below the minimum permitted size hole. So in this case you have to just ensure, see this dotted line, dotted elliptical hole is not coming inside the inner bolt circle, it is not coming inside here. That's why the go end of the gauge is going to pass. What is happening? Go end of the gauge is going to pass, because the minimum size of the actual hole is not less than the minimum permitted size, isn't it? This hole is not crossing this here. That's why the go end is going to pass. So go end is passed, that's why one condition is satisfied, isn't it? The go end should pass. Now let us say that now you come to the no go end. This is, let us say this is a no go end of the gauge. Now if you try to insert this no go end in this hole, in this elliptical hole, now you just tell me whether the no go end will pass here or not. You can see this is an actual hole. So if you try to insert this size, this outer circle represents the no go end, inner circle represents the go end. As you can see, the outer circle is larger than this dotted line, isn't it? So this outer circle is the no go end. So no go end size is larger than the actual elliptical hole. That's why the no go end is not going to pass, isn't it? No go end is not, this is the no go end, remember these two sizes. The no go end is not going to pass, isn't it? So second condition is also satisfied. When you try to insert the go end is passing. Then second condition, no go end is not passing through this elliptical hole. So the second condition is also satisfied. Since both the conditions are satisfied, what it means? It means that whatever hole you have produced, elliptical hole produced, that is okay. But in actual reality, is this elliptical hole accepted? Is it okay? It is not okay. It means that this gauge, whatever gauge you are using, this gauge is giving you the false result. This gauge is giving you the false reading, because this elliptical hole should have been rejected, but because of the cylindrical shape of the no go end, this hole is getting accepted, because go end is passing, no go end is not passing. That's why it is as per the gauge checking procedure, this hole is getting accepted, but it should have been rejected. Then now let us say if we follow the Taylor's principle, what is happening? Now as per the Taylor's principle, the no go end should be made in terms of the, rather it should not be made as a cylindrical. The no go end should be prepared in terms of the sharp points. Now see, if you try to pass uh, uh, the go end is going to pass here. Cylindrical go end is going to pass. There is no issue with the shape of the go end of the cylindrical gauge. Remember that the go end should be cylindrical. There is no issue. So if you pass the go end through this hole, it is going to pass. But if you make the no go end in terms of the in like the 2 points, then what will happen? See here, if you press the no if you put the no go end no go gauge here, it is not going to pass. But if you rotate this no go end and if you measure the dimension over here in this position, so what is going to happen? In this case, you can see the size of the no go end is less than the size of the hole, isn't it? The size of the actual hole is larger than the size of the no go end. So in this position, the no go end is going to pass. Why? Because the no go end shape is in the form of the 2 points. So here the go end has passed and no go end has not passed. That's why the hole is rejected. 1 minute. जरा आवाज कमी करणार का? So as you can see, as we have made the no-go gauge in terms of the 2 sharp points, this hole is rejected. So here is the importance of the Taylor's principle. Okay. So since the Taylor's principle is followed, the hole is rejected. It should have been rejected. So that is the importance of the Taylor's principle. But whatever Taylor's principle we have discussed, there are some practical difficulties to implement the Taylor's principle. What are those practical difficulties? Go end, if we make the go end equal to the size of the hole which we want to check, then the go end will be too heavy to handle and it will be costly also. Okay. So suppose there is a shaft, there is a part whose diameter is say 2 meter and say its length is say 500 mm. So just imagine if you want to check the sizes of this component, you have to make the go end whose diameter is say what I told diameter, it is say 1 meter and its length is 500 mm. So see how big go end will be. That will be too heavy, you cannot handle it. It is very difficult to handle and it will be costly also. Secondly, if you make the no go end with sharp points, it will wear out very quickly, because as per the this Taylor's the no go end should be made with the 2 sharp points. So these 2 sharp points will get worn out very quickly. So practically it is very difficult to implement the Taylor's principle. So one practical solution is done. Taylor's principle is not actually used in the common practice. So practical designs of the gauges often differ from the true forms specified by Taylor's principle. Generally, what is happening? Generally, with the satisfactory machine tool alignment and bearings, means if your machine tool, that is a lathe, milling machine, water drilling machine, if its alignments are satisfactory, if your bearing alignments are good, then geometrical errors produced by machining are relatively very small and common type of the gauges give satisfactory result. Means what? Because there are some practical difficulties with the Taylor's principle, the gauges are made in cylindrical shape only, and go end of the gauge is also not a full form gauge, only it is a part form gauge. So that's why it becomes less weight also. But it is applicable provided that your machine tool alignment and bearings is satisfactory or good. Then in that case geometrical, it is observed that the geometrical errors produced are very less, and you can use the common type of the gauges. So we will stop here, and in the next lecture we are going to actually see the steps to design the limit gauges, what steps are required, and after that we will see the minimum two numericals, actual two numericals on the design of the gauges. Thank you.